I am Morteza. I'm a PhD student from University of Minnesota. And as a part of my PhD thesis, I worked on basically the topic of learning from big data. During the course of my research, we have developed various data analytics to unveil the anomalies in social networks, to map out the traffic in internet protocol networks, and also to accelerate the acquisition process in MRI to basically make the time for the patients to stay in the MRI magnet shorter. So in all these applications, we are typically faced with large-scale data sets which are streaming over time, like the likes that we make in the Facebook, and also they are spread like the network data, and they're contaminated with outliers, and a lot of a big fraction of data might be missing. So we are typically faced with ill-post problems, and we are trying to leverage the low dimensionality of the data in terms of sparsity and low rank to make the ill-post problem well-post. So one of the models that we have looked at is decomposing a matrix Y into a low rank plus an innovation, which is a sparse across some dictionary. If you think about it, this model appears in a lot of applications where you usually have a signal, which is a superposition of a low rank background, and an innovation part, which is a sparse across some given known dictionary. Okay, we have spent quite some time to understand this model and to try to solve the problem of identifying X and X0 and A0 when we are given Y and R. So we have studied identifiability for this problem, where we relied on the convex estimator P1, which tries to fit the data to the model in the least squares terms, and it promotes low rank for the data through the nuclear norm term, which is some of the singular values, and sparsity for the basically matrix A through the L1 norm. So for this problem, in the absence of noise, we have established that under certain conditions, on the sparse and low rank matrices, then one can exactly recover the unknowns. So this proves the basically capability of this algorithm in terms of returning accurate estimates. And here is a test for validating the data with basically validating the exact recovery estimator with synthetic data. But let me show you a more interesting example, a motivating example, which comes from the backbone of internet protocol networks. In IP networks, typically there are some origin to destination flows, for example, a flows which goes from San Diego to Minnesota. This flow will travel across several links, but the problem is that these flows, because of some viruses or some cyber attacks, they have some spikes. So, and we are looking after these spikes. But the problem is that we don't have access to all the pairs. What we have available are some link measurements, which are superposition of the OD flows. Now, if we collect the measurements of all link across T time slots in a matrix Y, then we will end up with a model, a low rank plus compressed sparse matrix plus noise, which is similar to the model that I motivated at the beginning. Here R refers to the routing matrix, which is a fat matrix, because in the network, typically number of flows is much larger than the number of links. So here, we know that the traffic is a low-rank matrix because of common patterns in the traffic and periodicity, and anomalies are sparse. And here is a test when we run the algorithm for the real data that we get from the backbone of internet to network. So this plot, the right-hand plot, shows the A0 and A hat. Basically, this is a map of anomalies across flows and across time. And you see that whenever there is a significant anomaly in blue, you know that you see that our estimator, the red one, picks that anomaly accurately. Okay, so another basically aspect of my research is to develop algorithms to solve for the estimates in this problem. So, and here we have looked at a more general model. We have a streaming data. We don't have the data as batch available. So we get the data sequentially over time, and here we allow that because of some dynamics in the system, the dictionary matrix R is changing over time. And also on top of that, we assume that a big fraction of the data is missing. At this time, we have only a small part of the entries of the vector YT. For example, if you think of it as link counts in the network. So and our goal is that we are given the past data and we are looking after a real-time estimate of XT and AT. Just think of in the context of anomaly detection, if we can find AT, it gives a real-time identification of the anomalies, which can be used to basically to avoid the anomalies in the network. So one of our contribution here is that since in our benchmark formulation, it's hard to solve the nuclear norm problem in an online fashion, then we leverage a separable structure of the nuclear norm, which basically is a nice characterization of the nuclear norm here. So I strongly recommend you to look at this because it has a lot of useful features. If we use this characterization in the formulation, then we will end up with an online formulation, and we have developed online algorithms based on theory of alternating minimization, which are provably convergent, and they work well for identifying the anomalies of backbone networks in real time. As a generalization of tensor matrices, basically we have developed online algorithm for tensors. Just think of the motivating example where you get a sequence of images over time. Okay, but you don't take the entire image, you get a subset of pixels. A motivating example is in the context of dynamic MRI. So, and the goal is to interpolate the misses in a tensor. So the good thing, one nice feature of tensors is that as opposed to the matrices, which basically lose the structure of the vectors, which lose the structure of the image, keeping the images as slices of a tensor somehow preserves the structure. So then we can leverage the structure. So then along the lines of the online formulation for matrices, we have developed online algorithms to track and learn the subspace of the tensor, and as a result of that, interpolate the tensor misses and basically perform other inference tasks for reduced dimension tensor data. So here is a test when we apply our algorithm to a real in vivo cardiac MRI dataset. Here you see this is a ground truth image, and this is the reconstructed image if we have access only to 10% of the data. You see that this tensor model can lead to significant acceleration. Also for networking applications, where we don't have all the data as a batch available in a single processing unit, we have also developed algorithms. Imagine the case that you have only a subset of rows of Y in each node. Let's say each row corresponds to a node. Then in this case, again, non-separability of the nuclear norm makes it challenging to solve P1 in a distributed fashion. Again, one of our nice contributions is to leverage this factorization and basically this characterization of nuclear norm through matrix factorization to end up with distributed formulations which are very simple, and they can basically lead to very simple algorithms with very low computational task per iteration. But one nice thing about this distributed algorithm is that although this problem P4 is a non-convex problem, because what we got after making it separable, the nice thing is that we have proved that under certain mild conditions, if the ADMM algorithm that we solve to solve this problem converges, then it will go to the global optimum of the original batch problem. So it's like that in a network with the nodes which are very simple, we can solve a huge scale problem when like the case that we have all the data available at a very at a single processing unit with a powerful processing resources. Okay, that's all. Thanks for your patience.